Hello, I am Shane Brinkman Davis Delamore, and this is Code and Optimism, a show where I explore how to solve problems faster with software. Today's topic is code quality. How to write refactorable code. I've been spending a couple episodes talking about refactoring, and this is a bridge episode to many other topics. I want to talk about code quality, and here's why. Let's dive in. First, we're going to talk about why does code quality matter. Code quality matters because we want code to be easy to work with. We want it to be easy to understand. We want it to be easy to change. We want to be able to open up code, and if we haven't worked in it in a while, or if we're new to the code, we want to be able to quickly understand what's going on and feel confident that we understand what's going on. And if we need to make a change, if we need to add something, we need to refactor, we need to add some features, we need to fix a bug, we need to make it so it's easy so that we can make those changes quickly and get about our day in terms of solving problems faster with software. All this matters because if we're never going to open our code again, if we're never going to edit again, if it is completely something that no human will ever look at again, then code quality doesn't matter. Code quality is exactly that bit that matters because we're going to open it as human beings and need to do something with it. That's what the code quality means, and that's why it matters, is because most code is alive. If we're using it, we're going to need to be able to update that code over time. So when I say code quality is refactorability, what does that mean? Refactorability is this aspect of being able to go in and edit our code. I like using the term refactorability because it kind of implies being able to do big, complicated edits on our code. But really, it's any type of edits we might want to do to our code. That's what code quality is about. How easy is it to edit our code? So, writ large, code that is easy to edit. So, for a given change, it should be obvious what we need to do in order to make that change happen. It should take the minimum number of edits to make that change. And those edits should be concentrated as close as possible to each other. If we have 3 edits, but each edit is in a different service that is deployed differently to a different location in the cloud, then there's a whole slew of things you need to check before you do all that change to make sure that's correct. Versus if those 3 edits are in one file, in just one component that's deployed independently, you can have a lot more confidence that those edits are not going to break things. And that leads to a general principle that it should be hard to screw things up with the changes you need to make. It should be easy to be confident that your changes are not going to break things. You should not incidentally break things you do not expect to break. And last, it should be easy to validate that the requirements are being met on your project. That there's going to be new requirements, whatever the changes you're making. There's going to be existing requirements. It should be easy to validate that everything is correct when you're done with your edit. That's what refactorability means writ large, and that's what code quality is all about. So now to the meat of the matter. How do we maximize refactorability? I think it falls into 2 major categories. One is maximizing code isolation, and the other is minimizing code size. So for maximizing code isolation, really what we're talking about is modular design. As we just said about refactorability, we want to be able to make a change in one spot and not be afraid that it's going to break anything else. So when I'm changing one module, all the other modules should be strongly isolated so that they're not going to get impacted by my change. Or if someone edits some other module, they're not going to impact the module that I am dealing with. As I'm saying here, this is a future episode topic. I've mentioned this before. If you want a sneak preview, go and Google the 5 essential elements of software modular design. You'll find my article. I'll also put a link down in the show notes. Minimizing code size comes into 2 major flavors, and I kind of find them, they're an analog of the computer science analysis of performance. There is the big O, or asymptotic performance analysis of algorithms, which is how does it scale? What's sort of the broad strokes of how this algorithm is going to work in the world? And then there are the constant time factors, which is this code. We have a couple extra bits of lines of code inside the inner loop, and it makes it run slower. So at the high level, we have what I like to say 0 extra n's, where n is something that you're counting. And the two most obvious ones is 0 extra features and 0 extra engineering. 0 extra features is kind of like the concept of the MVP, or minimal viable product. You don't want to add any features in that aren't essential for you getting out the door and moving forward. Again, this is really a topic for a future episode. But if you are putting in features that you're just guessing at, chances are you're going to guess wrong. You're going to spend a lot of effort building a feature. You're going to make your code bloated and more complicated, which means harder to refactor later. And the users are not going to care because you made a guess without validating it with the users. So that's sort of the product level. Also, 0 extra engineering, of course, means don't over-engineer things. Don't get into premature optimization. Don't make it capable of scaling to 100 million users when your target audience is Fortune 500 companies. By definition, there's only 500 of them. These are the type of things that you want to minimize at the sort of overall architectural level of your project. But then there's also the more tactical, minimizing the overall code size. So assuming that you minimized your architecture, either it's the product level in terms of features or at the engineering level in terms of the overall architecture of the system, now you're getting into actually writing code. And I think there's two main things that I look at when I'm trying to minimize my overall code size. The most important one is don't repeat yourself, dry. One of the most powerful concepts I've seen in software engineering ever. In fact, I kind of think almost all software engineering concepts ultimately come down to dry. Again, a topic of a future episode, but I'll just give you a little teaser in that dry is not just about copying and pasting code. That might seem the simplest, don't repeat yourself. But what it really means is think of yourself as like a compression algorithm that looks for higher and higher levels of patterns in your code that are similar or repeated. So you might have written 2 different sorting algorithms and you realize, oh, wait a minute, they're both sorting algorithms. So then you go say, all right, I'm going to write one sorting algorithm and use it in multiple places. That is discovering 2 different patterns. And if you would have looked at the code might have looked quite a bit different for those 2, but you realize they're both just sorting. And so you're going to say, all right, I'm going to simplify that down to one sorting algorithm. Dry is a path of mastery with no end. You can always see bigger and broader pictures of patterns in your code and realize ways that you can reduce the complexity of your code by not repeating those patterns. The most tactical of this list is actually reducing your code size, and I like to argue to measure your code size in terms of tokens, because tokens are the minimum semantic unit of your code. Much like good writing packs a lot of semantics into every single word, same thing with code. You want to eliminate the noise by having a lot of largely meaningless tokens in your code, and you want to have each token expressed to the computer and to the human reading the code as much as possible about the problem that you're solving. Less tokens, of course, then means less to read. It means less to edit when you need to make changes. It's the fundamental unit of code size. But when you're measuring tokens as opposed to lines of code or total byte size, it doesn't lead to too many artificial inflation problems of, it's actually probably good to have, I like verbose variable names, for example. Tokens doesn't penalize you for having verbose variable names. It doesn't penalize you for having comments. One comment is either 0 tokens or 1 token, no matter how big the comment is. And it doesn't penalize you for nicely formatted code, like byte size would do, or it doesn't penalize you for having white space on lines, which line count does. Both line count and byte size, those are not tied to the semantics of your code. You want to minimize the semantical expression of your code, and that is tokens. So I like to play a game of token golf with my code as I'm writing it. I'm always looking for how can I express this solution with less tokens. So that's a topic for a future episode. So You might be saying to yourself, that's all well and good. Yes, maximizing code isolation makes refactoring easier. Reducing code size means it's going to be less work when you need to do that refactoring. But isn't there something you're missing here, Shane? What about correctness? What about performance? I will strongly argue that those are not code quality metrics. In fact, they have nothing to do with code quality, which seems like kind of an extreme position, that correctness has nothing to do with code quality. And to be clear, I mean code quality. Correctness does have to do with quality, but not code quality. Code quality is very specific to this concept of refactorability. The reason why I want to separate out correctness and performance and things like that is those are not code quality metrics. Those are requirements. They're requirements because there's no such thing as perfect correctness. There's no such thing as perfect performance. Any bit of code can be made more correct. Any bit of code can be made more performant. Now, I certainly think you'll probably believe me on the second one, but on the first one, remember in a previous episode, which I'll make a point to link to, I talked about the nature of truth in general, that there is no such thing as 100% truth. Similarly, there's no such thing as 100% correctness. It is not possible to make a perfectly correct piece of code. It is always possible to make code more correct, no matter how good it is in the first place. And you should not strive for perfect correctness. That's like striving for perfection. You need to strive for the right level of correctness for the project you are doing. And as an example, think about it. If you're making a proof of concept, the amount of correctness in that code is very different from the amount of correctness for a beta release, for an initial sort of user-facing user code release, or for maybe it's mission-critical rocket control software. Each of those has a different level of correctness, and if you think about it for a second, that is a requirement for those different pieces of software. That's not a question of the code quality. You can have good code quality for a proof of concept, you can have good code quality for beta, you can have a good code quality for your rocket control software. Same thing goes for performance. And in fact, it's dangerous to think of those as code quality. It's dangerous because code quality should be something that we should continually be trying to make better. But if correctness or performance is in that camp of code quality, continually trying to make those better is going to lead directly to over-engineering the problem and premature optimization. If you just in principle are going to continually try to make those better, you're going to overshoot the targets of what you're trying to build, which means you're going to make the system bigger than it needs to be, which is basically going to actually hurt refactorability, and you are going to actually overbuild it in the wrong way, so that when the requirements change, it's going to be harder to get it all done, to make those requirement changes. Refactorability really should be all about stuff that we are going to continually improve to make it easy to continue to improve the software. It's a bit of a virtuous cycle. So, in conclusion, code quality is always and forever refactorability, our ability to understand and edit our code. It needs to be easy to work with, easy to understand, easy to edit. The main strategies is both maximizing the isolation of various parts of our code using modular design. It's a very deep and important topic we're going to get into later. Much like the other things I've touched on, it is a path of mastery that you can always get better at. And minimizing your code size, both at the product level in terms of features, at the architectural level in terms of engineering, and at the tactical level in terms of the number of tokens it takes to implement your solution. Now, with all that, I want to ask you for your thoughts. And specifically, all of these refactorability strategies they're kind of like predicting the weather. We don't, by definition, know how the code is going to need to change in the future. So when we try to make the code easy to change, we're making a prognostication, we're making a guess, we're trying to predict the weather about what the changes we're going to need are in the future. And so we're making our code in general easy to make changes to, in terms of the changes we've generally seen in the past that are generally likely to happen. But of course, that's never going to be perfect. There's huge rooms to improve that because there's all kinds of different ways things can change in the future that we cannot possibly anticipate. So I would love your thoughts in particular on this maximizing code isolation versus maximizing code size. Is there more ways to maximize isolation, more ways to reduce code size, or is there other ways, minimizing code size, right? Is there other ways to make the code easy to refactor for potential future refactors? And maybe there's things that are problem domain specific. This is what I've covered as more general application. I'm also curious what your thoughts are about me putting performance and correctness into requirements as a category and separating them out from code quality in terms of how we think about things. So let me know below in the comments. I'd love to hear your perspectives. I only have one angle on this mountain. I want to hear your perspective. So thank you very much for spending your valuable time with me. And remember, all problems are solvable with enough knowledge.